Hey everyone, thanks for tuning in. We're going to look at the accuracy and precision lab today. So this is a pretty neat lab where we're going to take some different bits of glassware and see how accurate and or precise they are. So first up, what's the difference between accuracy and precision? Well, accuracy is how close the measurement is to the true value. Precision is how close the measurements are to one another. So you can imagine you can be one without the other. For instance, let's say we've got an object that has a true mass of 10 grams. Maybe it's a calibration weight we've bought. And we do 4 trials and we measure the mass 4 different times. So we get 10.49 grams, 9.79, 9.92, and 10.31. On average, that weighs 10.13 grams. So we would say because on average, this red dotted line is higher than the true line, we're going to say that this is inaccurate. So we can also speak about the precision. The 4 masses are quite far apart. There's quite a big spread from a high of 10.49 to a low of 9.79. So that's over half a gram spread there, right? That's 7/10 of a gram. So we're going to say that's not very precise as well. But imagine a different student measured these 4 masses here. You can see they're quite close together. So we would say they're very precise measurements, but they are below the true mass of 10 grams, so not very accurate. Whereas the third one here might be hopefully what we see in the lab. On average, it comes out to be very close to the true mass, so it is accurate. And the variances are quite small, so that means it's very precise. So that would be a perfect situation to hopefully that you will see in the lab. Some people prefer the dartboard analogy, and so if you make 4 dart throws and they're all centered, that's a very accurate throw, and if they're close together, that's very precise. Whereas this is one where they are all about the same spot, but they're different than the target, so it's not an accurate throw, but they're close together, so that's quite precise. This one, counterintuitively, is actually a reasonable throw. It's quite accurate. It sort of averages out in the center. The 4 throws are sort of averaging out around the bullseye, but they're not very close together. And this one over here is terrible. It's neither an accurate nor precise. We're going to be looking at 3 bits of glassware today. This you have in your locker, a 50ml beaker. This you also have in your locker, a 10ml cylinder. This you will be provided with for the lab, and you need to return it when you're done. So it's a 10ml syringe. We're going to call them glassware, even though obviously this is actually made of plastic. So here's the procedure. We are going to do this with 3 different bits of glassware. We're going to take our beaker. Our beaker looks something like this. And we're going to pour water into the beaker until it is exactly at the 10ml line. And so you're going to have to be very careful to get it to the 10ml line. And you're going to pour the water in until it gets up to the line. If you are a little bit below, you can take a little pipette and you can suck up a little bit of water into the pipette and you can drip it in there. And if you're too high, then you can use the pipette to suck some out. So you're going to basically fill it up to the 10ml line. So this becomes your measured volume. Okay. How do you know how much it really is? Well, you're going to weigh it on a balance and you're going to record the mass, and maybe the mass comes out to be, oh gosh, I don't know, 9.983 grams. Now, how do you do that? You're going to weigh the beaker full and empty. So you're actually going to weigh the beaker empty. Maybe it weighs, I don't know, let's say it's something crazy like 10.000 grams. And then you're going to weigh it full. Maybe it weighs 19.983 grams. And then you're going to subtract one from the other. In fact, I think I've switched these around, haven't I? So you're going to subtract, and you can see it's 9.983 grams. Now, you want to pay attention to your subtraction. So if this has 3 digits after the decimal, and this has 3 digits, then your final mass has 3 digits. So that is the true, if you like, mass of the water inside your beaker. Now, how do you convert it to a volume? Well, the way you're going to do that is you're going to use density equals mass over volume, and you can rearrange and show that volume is mass over density. So what we need to do is to take that mass of water and divide it by the density. And how are you going to find the density? Well, we actually have a lookup table in our textbook. So let me go ahead and show you the lookup table. So this is what the lookup table looks like. So the density actually changes with temperature. So you're going to have to actually measure the temperature. If the water temperature is about 23 degrees C, so 23 degrees C would be right about here. So you're going to kind of walk up and you're going to find this line. It's going to go right over here. So it is, oops, kind of a little bit squirrely there, isn't it? So that would be 0.997, and let's say it's slightly above there, 55 grams per milliliter. And so notice we can write per milliliter, 1 over milliliter, right? And we can also write that as milliliter to the -1. So when we have grams over milliliter, okay, that can be written as grams milliliter to the -1. So now we have the density here of our water, so we can find our mass. We can find our volume, right? So if density is mass over volume, then volume is mass divided by density, and we can just look up our mass and look up our density and plug them in. So here we go. So this was 9.983 grams. The density we figured out was 0.99755 grams per milliliter. We'll write it as grams divided by milliliter. What about our units? Our grams cancel out. We've got 1 over milliliter. So if you take the reciprocal of a reciprocal, you're right back to where you started. So that would have units of milliliters. And we just need a calculator here. But before we go on, we should check significant figures. The top has 4. The bottom has 1, 2, 3, 4, 5 significant figures. That leading 0 doesn't count. So at the end of the day, we should be rounding our final volume to 4. And if we plug that in on our calculator, we get 10.01 rounded to 4 significant figures milliliters. So that would be our true volume. So we had a measured volume of 10.0 mil and a true volume of 10.01 mil. So they're quite close. So we know it's probably accurate. Of course, until we make more measurements right, we really can't be sure if it's accurate or precise. So we're going to do it in triplicate. So we're going to go ahead and we're going to dump the water out of the beaker, and we're going to fill it up again and reweigh it and redo the calculation. And Bob's your uncle, we can turn that those masses that are full and empty into a mass of water, and we can go ahead and use the density at the temperature to find the volume, and then just compare and look. So we should talk about reading the volume here. And so this is a typical scale. So this is a 50 mil line, and this is a 60 mil line. This is probably a 100 milliliter cylinder. And what we see is that when we fill it with water, the water actually kind of rises at the edges and flattens out in the center and rises again in the edges. The water molecules are attracted to the glass, so they actually rise up slightly at the edge. We're always going to read by looking at the very bottom of that surface. We call that surface a meniscus. So meniscus is literally like a skin, so maybe I'll write that in red. So meniscus. And when we look at it, we always want to look at it side on, and we want to be level with the bottom. So we're going to look at it side on like so, and we can see the very bottom is right about here. So I'm taking this as being the very bottom, the dark portion. Sometimes I like to put my hand behind here, because if you put your hand behind here, it kind of, the reflection of the skin on the bottom of that meniscus makes it a little easier to see. Now, how would we measure this? Well, if this is, remember we always measure to 1/10 of a division. And so what are these divisions here? Well, this is 50, and this is 60, and there are 9 lines in between, so there's a total of 10 separations here. So that means that each one of these represents a 1 milliliter mark. So this is 51, this is 52, this is 53, and so on. So we're going to measure it to tenths of that. So we have to go ahead and say, how many tenths of the way between the 52 line and the 53 line are we looking at here? And I think we are about 6/10 of the way up. And so this is going to be 52 and 6/10 of a division. So 52.6 milliliters would be our final volume here. So I'll write that on white. I think that's a little bit easier to see. So all of the things that you're going to read today, you're going to have to be carefully reading the scale to get it exactly, I think in our lab, at 10 milliliter mark, sorry. Here's another scale. Maybe you can try and read this. So just go ahead and pause this video and read it and see what you come up with. Okay, if you unpause it now, let's see if we get the same answer. So you're going to look at the very bottom here. So that's going to be roughly there. And you're going to say maybe that's 2/10 of the way between this line here and this line here. So we're about 2/10 of the way up here. So what do we have here? So this is the 6 mil mark. This is the 8 mil mark. So this is the 7 mil mark. And let's see, there are 2, 4, 6, 8, 10. So this is 6.2. This is 6.4, so you can see each division here is 6.6 is 2/10 of a mil, and so we need to know how much of the way are we between the 6.6 and the 6.8. We're 2/10 of the way through, so 2/10 of a division, so 2/10 of 0.2 is 0.4 of a division. I'm sorry, that's not right, is it? It's 0.04 of a milliliter. So we're just going to add that. So it's 6.6 plus 0.04. So that is 6.64 milliliters here. So we have to be very careful here. So this is 6.2, 6.4, 6.6, and this is 6.64. So it's kind of challenging to read this closely, but with practice you can get there. Again, in the lab, we're going to be working with a balance. We're going to be working with a balance that weighs out to a milligram, and this is actually very similar to the balance we have. I think ours is a Mettler PE 200, but this is a 360, very similar. And there is a bar on the front, and you basically press the bar to zero it, and if you lift it up, you turn it off, and if you push it down, you zero it. If it ever doesn't read zero when you first come to it, you can just push that bar until it reads zero, and then essentially you just put your object on top. And the cool thing about the balances is that these balances cost about $1,000, and so we can assume that because this balance is well cared for and calibrated, this mass is the true mass. And so when we use the true mass and the true density, we can find the true volume, and we can compare it to the volume we get by reading the side of the scale. So this is the data sheet that you'll fill out. The top part is really sort of what you measure directly, and the bottom part is what you calculate. So the temperature of water, you should be reading your thermometer to a tenth of a division. So maybe it's 22.3 degrees C here. Notice we're dividing out the units here, so that just changes that into a pure number. And then you would look up from your table whatever the density of water was at that temperature. You would try your best to interpolate between the 22 and the 23 mark, let's say. And then at the top you would write your empty masses. So maybe the beaker weighs, I don't know what it weighs, 25.101 gram here. And you only have one spot here because you're just going to measure it empty, and you're going to be using the same beaker throughout, so it really isn't expected to change. And then you're going to pour water in there until you reach as close to the 10 mil mark as you can, and you're going to reweigh it on the balance, and maybe on the balance it weighs, 36.211 grams the first time, and you dump out the water and you refill it and you reweigh it, and maybe it weighs 36.231 grams, and then you dump it out and you reweigh it, and maybe it weighs 35.911 grams, let's say. And you do the same thing for your cylinder and the same thing for your syringe. And then underneath you're going to go ahead and complete the table. So everything in data table 2 is a calculation. These ones that are asterisks are ones that you've got to show your work on the next page. So let me go ahead and show you what this would look like. So this would be your full 36.211 grams minus your empty. So that's 25.101 grams. And your calculator is going to say something like 11.11, and that's actually wrong. And the reason it's wrong is because when we subtract, we go by digits after the decimal. And so if these have 3 digits after the decimal, the final answer has to have 3. So even though your calculator won't display the last 0, you have to put it in, and of course you have to write the units in. Now, because we are dividing the units out here, we don't have to keep writing them in, so we can just write 11.110 here. You would do the same thing here and the same thing here, and then underneath here you would turn it into the true volume. So there's a little asterisk there. So again, density is mass over volume, volume is mass over density, and so you would take your mass here. This is the mass of the water, by the way, so remember, we don't want the mass of the beaker included, right, because the beaker's not made of water. And then the density, let's say the density was maybe 0.9999 grams per milliliter, which it probably isn't. But again, you can do the unit calculation here, so the grams cancel, and you're left with milliliters. And if I type that in my calculator, I get 11.11, and if this was the correct number of significant figures, this would have 5 and this would have 4, so the final answer would have 4. I'm actually not sure that's the correct number of significant figures. I think your densities, you can probably read off more precisely than that. And at this point here, we would write that in the box. That would be 11.11. And again, we don't write milliliters because they are already divided out here. And we would have our second mass. We would subtract away from that the empty beaker, and we could use that mass here and divide by the density to find the volume, and we would place it here. We would do it a third time, and then we would average them out. So we would essentially be adding them all up and dividing by 3. Now you might say, gosh, if I divide by 3, isn't that one significant figure, right? So imagine I had 11.11 and 11.21 and 11.31, and these were, all grams, and then I divide all these by 3, right? You might say, well, 3 has one significant figure. Well, it does, but because this was a counted number, actually, you've got to remember that it has not one significant figure, it is exact, so there's no error at all. And if you look at the top there, you are dealing with things that are being added up, so you go by decimal places, so that would be 33.0 let's see, 3 of a gram, so 2 decimal places. Okay, and then when we do the division by 3, now we go by significant figures. So this has 4 significant figures, and this has an infinite number. And if I go ahead and take that, 33.63, and divide by 3, I get 11.21, which I probably should have known. Actually, I made a mistake here because all of these are not grams, are they? They are actually milliliters. So I should have written milliliters for each one of these because I'm looking at a volume. And of course, we're dividing out the volume here. So it would be, just 11.21, just as a raw number. So that is what the datasheet should look like. Now on the very back page, you got a couple of questions here. So one is going to be explain what was the most accurate piece of glassware. And so that'll be the one where the average true volume was closest to the 10 milliliters. You're going to calculate that using percent errors. So rather than just saying, well, this one was closer than that one, you're going to calculate the error. And so you're going to take the measured value, which is what you read off the side of the beaker or the syringe, which is 10 mil, minus the true value, which is the value for the volume you get from taking the mass and the density, and divide it by the true value. And these bars here mean the absolute value, so whether the measured value is higher or lower, we're just going to ignore the sign, and that will just be a fraction times by 100 to make a percent. So we're going to try and hopefully see which one's the most accurate piece. The one with the smallest percent error should be the most accurate. And then we're going to explain which is the most precise one, and we're going to calculate what's called the RPA. And on the intro to the lab, it explains what an RPA, essentially the RPA stands for range as percent of average. So the range is the difference between the biggest one you got and the smallest one you've got. So the less precise it is, the bigger the range should be. So as percent of average, we're going to go ahead and average out the values we get. So let's just add them all up, divide by the number. And then we're going to compare the range to the average. So for instance, if you had, say, oh gosh, let's just do it for 2 things. I don't think 2 things make sense, but let's say you got 2 measurements. One is 10 milliliters and the other one is 11 milliliters. Then the range, the difference between them is 1 milliliter. And the average, we can see, is just going to be adding them up, dividing by 2. So that's 10.5 milliliters. So the range as percent of average is going to be the range, 1 mil. Okay. We just care about the absolute value, divided by the average. So that is 10.5 mils. And so the units cancel out there, so it's just a fraction. And that would be a fraction. If we times by 100, though, that would convert it to a percent. So if I go ahead and calculate that, so 1 over 10.5 times by 100 is 9.5%. And the idea is that the bigger the range, the bigger the value on the top would be, so the less precise the glassware would be. So the bigger the range as percent of average is, the worse the precision is. Thanks for listening.